Hey everybody, we're back again with a new video. This one, we're going to be diving into Chapter 7 of Bioenergetics. Now, we've actually already talked a little bit about bioenergetics in previous chapters when we're talking about our exergonic and endergonic reactions, as well as the Gibbs free energy. But coming back to this now, we're going to take a little bit deeper dive into it. So our objectives are defining bioenergetics, explaining the role of ATP and O2 energy generation, describe thermodynamic principles to explain what determines whether or not a reaction will occur, and to what extent that reaction will occur within the cell, know the concept of free energy, changes in Gibbs free energy, understand exergonic and endergonic reactions, and their coupling in biochemical pathways in relation to change in free energy, heat content, aka enthalpy and entropy. Okay, so bioenergetics or biochemical thermodynamics. So this chapter is going to have a lot of reading. So we're going to go through as well as kind of taking some time to go over some vocabulary and some other information. So this isn't a super long chapter, but it is a little bit information heavy, so we'll make sure to get through it. Okay, so bioenergetics is the study of the energy changes related to biochemical reactions. This explains why some biochemical reactions occur and why some reactions do not occur. Biological systems use chemical energy to power the living processes. Okay, free energy, aka Gibbs free energy. This is what big one that we want to know. Thermodynamically, free energy is defined as the energy content in a system that can be converted to do work at a constant temperature and pressure. Okay, so a couple things we want to break down in this really quick. We want to look at in a system. So when we're talking about a system in biochemistry, you want to think of it kind of like an enclosed space. So for example, you can treat each, like where a reaction is occurring or where a group of reactions are occurring as almost like it's a little box around that material of where all that's occurring. That little box and everything that's contained inside of it, we call that a system. So in the system, really, it can be like an actual physical thing, like for example, your body. If you think about your entire body, your body is a system. Or you can think of it more figuratively, just as like these specific components or these specific compounds are interacting with each other at this point, and we're just looking at that very specific zoomed in spot, and you can call that a system as well. Okay, just understand that within a system, nothing is leaving or getting added unless otherwise stated in the problem, okay? And now we're going to talk that the energy can be converted to do work. Work in the sense of biochemistry. Let me pull up a good definition. We'll stick with this one. That work is the energy required to move an object against a force. Okay, moving an object against a force. That'll be important a little bit later on. Understand that work, or the energy that we're going to be talking about is we're going to be talking about it measured in joules. Okay. And that'll come back to us later on. And this as well. We'll use joules, and then actually we'll also see a quick correction here. So energy itself. Energy will be. We'll talk about with energy, but specifically with work. Work is in joules, and 1 joule equals 1 Newton through 1 meter. I believe it is 1 Newton per meter. Something along those lines. That might not be 100% accurate, as these units are a little bit fuzzy for me right now. But as we get back through everything, we'll get into that a little bit more and make sure that that's correct. But understand that we'll be looking at joules, we'll be looking at newtons, just understand all of those. If you see those units, that is going to be, those units are going to be talking about energy, okay? And then constant temperature, pressure, we're always assuming that we're at a constant temperature and pressure. There are specific, like pressure, the typical pressure is 1 atmosphere, or about 760 millimeters of mercury as a pressure, but we'll get into more of that later on. Okay, it is the useful energy. It is denoted as Gibbs free energy. Every compound contains its own free energy content. Okay, keyword there is compound. Energy is stored inside of bonds. So when a compound has bonds, when bonds break or when bonds form, we are releasing or bringing in energy away from the system. Okay. In biochemical reactions, energy is released from the breaking of chemical bonds when a compound is metabolically degraded. Okay. So breaking of chemical bonds releases energy. Okay. And we'll get more into this later. When energy gets released, it usually comes off as heat. So when energy gets released, you get an increase of heat in the system. Increase of energy in the system increases heat, and that'll be our exergonic. Okay. But when a compound is metabolically degraded, simultaneously, when a new compound is synthesized, the released energy from a broken compound is used to construct it. Thus, new chemical bonds are formed, and the energy is trapped in the form of a chemical bond. So the saying is, we'll have a chemical bond break, and the breaking of that chemical bond releases energy. That energy that has been released is then used to form a new bond. Okay? It's a multi-step process. Hence, biochemical reactions that include breakdown of molecules and synthesize new molecules involve coupling of energy release and energy utilization. Thermodynamically, when energy is released in the catabolic pathway, we've seen that word before, catabolic pathway, or catabolic, or catabolism, or think back, remember that word. Remember catabolic, it's one of those words that I really struggle with. Catabolism, the sequence of enzyme catalyzed reactions by which relatively large molecules in living cells are broken down or degraded. Breaking down is catabolic. Or in an individual reaction from the breakdown of a chemical bond, the reaction is termed as exergonic. Please make that connection, that catabolic reactions are exergonic. Word for word, that will be a test question. Either or the other way. And the opposite of catabolic is anabolic. Anabolic will be the opposite. It will be our endergonic. Whereas when new chemical bonds are synthesized in the anabolic, there it is, next line, anabolic pathway, energy is trapped in bond formation and the reaction is termed as endergonic. The summation of all the catabolic and anabolic pathways is overall known as metabolism. Practically, in all metabolic pathways, exergonic and endergonic reactions are coupled, meaning that they go together. Okay, free energy is the useful energy in a system. So a change in free energy represented by the delta, remember delta means change. A change in free energy is the portion of the total energy in a system that is available for doing work. It is the useful energy. The ground state energy of the compound, G1, that is undergoing breakdown is higher than the ground state of the product. What this means is that if we have a compound right here that we are breaking apart, right? Let's say the amount of energy released is going to be 5 units of energy, okay? When it goes that amount of energy that is now available to create a bond, when it creates a product, okay, new bond forms, the amount of energy that goes into that bond has to be less than 5 units of energy. Okay? So our end state, our product, the amount of energy found in our product is always going to be less than what we originally had in the original compound. Okay? So the difference in the ground state energy between the reactant G1 and the product G2 is our delta G. So G1 minus G2 equals delta G. So writing this out, the initial energy in the first compound minus the initial energy, or the energy in the final product, gives you delta G. What that is, delta G then literally is, so our delta G equals the amount of energy either increased or decreased within the system. I should say that is now available within the system. Remember to talk about the system, we talked about that box. So did we lose energy or did we gain energy in the overall system, okay? Or I should say, did we gain or lose energy available in the overall system? So free energy change in standard condition. Here's some of the standards: temperature 298, pressure 1 atmosphere, pH 7, concentrations of the reactants 1 molar, and that is denoted by delta G naught. Okay, these are all of these, the standard condition. These are kind of like the quote-unquote normal settings. Those are like the default settings for our reactions that we measure everything, just to keep it consistent, okay? Just because if we start to mess with those different things, then it becomes a whole lot more math and a whole bunch of other stuff. Okay. The laws of thermodynamics. He always will throw in a couple of questions on these, saying like, this is which law of thermodynamics, or it'll give you a definition and say which law of thermodynamics is this, those kind of questions. So the first law of thermodynamics: the total energy of a system, including its surroundings, remains constant. So total energy is constant. Energy may be transferred from one part to the other, and energy may be transformed to another type of energy. Kind of like going from a chemical bond to heat. Okay? Think about putting wood in a fireplace. When you put wood into the fireplace, combustion, which is a chemical reaction, the wood burns, it combusts, and then that releases heat and light. So you're taking the stored chemical energy within the wood and transforming it into heat and light energy. The second law of thermodynamics is the total entropy of a system must increase if a process is to occur spontaneously, and entropy is the extent of disorder or randomness of the system. I like to think of entropy as the chaos of the system. Okay, the way that entropy is going to increase is if you have more stuff in the system, more individual things. So for example, let's take sodium chloride, right? NaCl. When we have a bunch of NaCl, it has a set level of entropy. As soon as we put that into water, it's going to dissolve and break down into two parts, okay? When the sodium and the chlorine, in this case, split into two parts, you get Na and you get Cl. Previously, you had one molecule, okay, Now you have 2 floating around. That causes an increase in entropy. So the breakdown of stuff, breakdown of compounds, breakdown of molecules into smaller molecules, into more molecules, increases our entropy. Okay? Other things that can increase entropy are stuff like heat. So think about the things that increase reactions. So heat, increasing like more stuff. Those kind of things will increase entropy. Now, this is where words kind of sound the same. Enthalpy and entropy. Okay? Under conditions of constant temperature and pressure, the relationship between the free energy of a reacting system and the change in entropy is delta G equals delta H minus T delta S. I'm going to retract and say something different, I guess. For the purpose of this class, entropy is just when there's more stuff in the system, so when things break down. And enthalpy we will refer to the heat for the purposes of this class. There's a little bit more to it, but we're not going to go that deep, so we'll stick with that. Okay, so entropy is represented as an S, and enthalpy is represented as an H. Okay. And I would highly recommend, as we get more and more equations, write these out and write out what each of those things are. So delta H equals change in enthalpy. Enthalpy is the heat content of the system. Okay. So delta G equals delta H minus T delta S. Where T is the absolute temperature. That absolute temperature we learned was 298 degrees Kelvin. Under the conditions of biochemical reactions, delta H is approximately equal to delta E, total change in internal energy of the system. Again, this is just adding some more variables into there. This is just kind of some math stuff. So because delta H equals delta E, we can replace them in the equation. I would recommend that you know this question, know these variables, and know this equation as well, just like what it represents. Information achieved from the delta G values. So whether the reaction releases or requires energy. Remember, if it releases energy, we are thinking it is an exergonic. If it needs more energy, it's an endergonic. Releasing of energy is going to increase the heat of something. If it's sucking the energy in, it's going to get colder. Catabolic reactions tend to break bonds and release energy. Anabolic reactions tend to absorb energy. Okay. The amount of energy involved in the reaction as well as what delta G tells us, and the ratio of concentrations of the products and the substrates at equilibrium. So let us consider a chemical reaction in which a reactant S is producing a product P. This S is different than entropy, okay? This is a different thing that we're talking about, so don't get confused by that. At equilibrium, we can write the reaction equation as S goes to P and P goes to S, so they can go back and forth. Now, if the rate constant of forward reaction is K1, so meaning substance to reactant to product is K1, and the rate constant of the backward reaction is K2, then the equilibrium constant for this reaction is described as K equilibrium. At standard condition, it can be written as KEQ. KEQ depends on the concentrations of the products formed and the reactants used. Thus, KEQ in that little doohickey equals the concentration. Remember, these brackets represent concentration. So the concentration of the products divided by the concentration of the reactants. From the thermodynamic point of view, at standard conditions, we can relate delta G naught with the KEQ. As this, we start getting into this equation, okay? R is one of the R is one of the constants, this universal gas constant, 8.315 joules per mole Kelvin, and T being that absolute temperature. Okay, so we have negative, the absolute gas constant, multiplied by temperature, the natural log of the concentration of the products, divided by the concentration of the reactants. This is a lot of math, a lot of big brain kind of stuff that's been figured out for us. I would recommend writing the equation down a couple times so that you can recognize the equation and knowing what each part represents, but you don't necessarily need to know how to solve this equation, okay? If you never need to solve this equation, you'll have a calculator and you just need to plug in these values, okay? Now, significance of the delta G values. If KEQ equals 1, so the products and the products and the reactants are equal, the concentrations are equal, then that reaction is in equilibrium. And that means delta G equals 0. If KEQ is greater than 1, then delta G is less than 0. So in this reaction, the rate of forward reaction is greater than the rate of backward reaction. So if we think about this, the forward reaction, so going from reactants to products, remember what we talked about earlier, how the products are going to have less energy in them than the reactants. So that a negative delta G, we're talking about our exergonic reactions. I'll pause and actually I'm going to say spontaneous reaction is a better way to put this. Spontaneous reaction, put out of your head that exergonic, endergonic stuff for one moment. A spontaneous reaction just means that the reaction going forward is more likely to take place. And then here, when delta G is positive, in this reaction, the rate of backward reaction is greater than the rate of forward reaction. Okay, and now we're going to get into what I was talking about before. If delta G is less than 0 or negative, it is an exergonic reaction or releases heat. If the value of delta G is greatly negative, the reaction goes virtually to completion and is irreversible. So if we have a really big negative number, so if we come up here with like a negative 200 for our delta G, huge number. I think even if it's like, I think the cutoff is about 50 if I remember correctly. That means that reaction, all of our reactants are becoming products. Okay, it's all going to the other side. Delta G, if our reaction proceeds only if the free energy can be gained, it is an endergonic or absorbs heat. So you'll get a lot of questions about endergonic and exergonic, okay? Talking about like this reaction occurs and the delta G is this. Would this feel cold or hot in the researchers? Or you'll have a reaction where you start to see steam come out of the reaction and it's really, really warm. Which of the following types of reactions are occurring? And that answer could be an exergonic, exothermic. It could be catabolic. It could be talking about bonds are breaking. Any of those things that are true about that reaction. Okay? So if the magnitude of delta G is greatly positive, the system is stable and little or no tendency for a reaction to occur. So this is why we also say that our very negative ones are spontaneous reactions, meaning that they're going to just spontaneously happen, and they're just going to keep happening until all of our reactants have become products. Now if delta G is 0, our system is at equilibrium and there's no net change that takes place. Standard free energy change. When the reactants in a chemical reaction are present in concentrations of 1 mole per liter, delta G naught is the standard free energy changes. At a pH of 7, delta G naught is denoted by delta G naught with the little doohickey on top. Delta G may be greater or smaller than delta G naught, whatever, depending on the concentrations of the reactants. So this is just getting a little more details of like the specific conditions and the variables, the way that the variables are written based off of very specific conditions. Okay. Endergonic reactions proceed by coupling to exergonic reactions. So synthetic reaction, for example, synthetic reaction, muscle contraction, nerve impulse conduction, and active transport obtain energy by chemical linkage or coupling to oxidative reactions. So coupling of an exergonic to an endergonic reaction. Conversion of A to B occurs with the release of free energy. It is coupled to another reaction in which free energy is required to convert C to D. So an exergonic reaction is occurring and releasing energy, and the endergonic reaction takes up some of that energy to form its product and do its job. And we also have additional heat that is let off. This is why when we work out, when we start moving, when we're moving and grooving, why our muscles actually produce heat. Because these kind of reactions are taking place inside of our muscles. And as these reactions take place, there is additional energy released in the system that is given off as heat, and that's why we heat up. Okay, the exergonic reactions are termed as catabolism, breakdown or oxidation of fuel molecules, and the endergonic reaction are termed anabolism or synthesis. High energy phosphates play a major role in energy capture and transfer. High energy phosphates are ATP, okay? Our ATP, the principal high energy intermediate or carrier, is ATP. A lot of this chapter is set up for the future, okay? We're going to talk a lot about ATP in the future. ATP is continuously consumed and regenerated. And we have a high energy phosphate on our ATP. So remember ATP, it stands for adenosine triphosphate, meaning that there are 3 phosphates, like 1, 2, 3. And then there's our adenine. ADP is adenosine diphosphate, so it has 2 phosphates. And then there's also adenosine monophosphate, which is AMP. Okay, so our ATP, ADP concentrations and cycle connects these processes that generate phosphorus to those processes that utilize phosphorus. ATP hydrolysis is the breaking down of ATP in some of that process, which we'll talk a lot about ATP and its uses and its function and why it's so important. One reason is that it releases a lot of energy. When ATP breaks down, it releases a ton of energy into the system to allow for things to occur. So there are 3 major sources of phosphorus taking part in energy conservation or energy capture: are oxidative phosphorylation, glycolysis, and the citric acid cycle, all of which we will get to later on in this book. ATP allows the coupling of thermodynamically unfavorable reactions. So this is another way he can put it. Unfavorable reactions are also aka non-spontaneous. Also our endergonic reactions are non-spontaneous. 2 favorable ones or spontaneous reactions, which are our exergonic reactions. So example, glucose plus phosphorus are glucose plus that phosphate, glucose 6-phosphate plus H2O, ATP plus H2O to ADP plus PI. The PI is just an ion, phosphate ion, okay? These are just a couple of those reactions for those. Remember, we noticed this one first before when we talked about glucose going into the muscle cells, right? Using that GLUT2 transporter. And that requires energy to get the glucose into the cells. Along with, remember, we talked about insulin binding and all of that good stuff. but still we're going to need energy to have this reaction take place to bring that glucose across. Hexokinase catalyzes this reaction that produces glucose 6-phosphate from glucose and ATP. Remember this enzyme. This comes back a ton, hexokinase. The net energy change is negative 4.0 kilocalories per mole. The change in free energy is essentially negative. This step is an exergonic and irreversible step in glycolysis. Adenylate kinase catalyzes interconversion of adenine nucleotides. Let me see how much exactly we have. Oh, this is the last thing. Okay, so this interconversion of adenine nucleotide has important metabolic significance. Since ATP is the major energy molecule required in numerous metabolic pathway synthesis of this molecule from other phosphorylated compounds are essential. Accumulation of AMP, we talked about this, AMP is adenine monophosphate, so 2 of the phosphates have been broken off, often occurs when ATP is used up and depleted. This makes a metabolic signal that stimulates ATP biosynthesis using AMP. So as we use up a bunch of our ATP, we're actually going to get cleaving or breaking off of multiple of those phosphorus, and we'll end up with AMP. So one of the phosphorus gets cut off of the ATP, and it becomes ADP, and then another one will end up getting cut off, and it becomes ADP. So when we have a high concentration of adenine monophosphate, the body's going to notice that, and it's going to stimulate making more ATP. So the reaction allows high energy phosphate in ADP to form ATP and AMP to be rephosphorylated to form ADP. ATP forms AMP plus those additional 2 phosphates. So these 2 can be broken off and energy is released. We'll get more into, like I said, we'll get a lot more into ATP later on. Other nucleoside triphosphates also participate in high-energy phosphate group transfer catalyzed by nucleoside diphosphate kinase. We'll get even deeper into a lot of this, like the UDP, GDP, CDP, later on. Mostly we will only talk about ATP and GTP are the 2 that you'll see mentioned. UTP and CTP we don't really get into at all. But yeah, all of these have the same exact function of storing that energy and releasing the energy in different parts of the body. But we'll only really focus on ATP and then a touch on GTP. Okay, and that's chapter 7. I will try and get chapter 8 out as quickly as I can for all of you. Hopefully you enjoyed this little chunk of material. Make sure you go back and review over a lot of these definitions. Write out these equations, kind of what each is saying. You'll get asked questions about the equations, maybe not necessarily how to solve them, but you'll get asked questions about the equations themselves. Okay? Good luck studying, and have a great day.